All right. Let's see where we go here.
I believe you're doing Smith chart this late in the day.
Oh, you didn't want to look at it for a while?
It's hard to find a good one like that.
Yeah,
See, that's got the SDR, SWR chart on it and everything.
really.
You could actually use that to solve a problem where the kind they show here is kind of useless.
Determine your stub matching parameters.
Isn't the one on here oriented incorrectly for what they're?
Well, it's not convenient, let's put it that way. This is actually one that you hardly ever see that has both the reactance and admittance. So it's both Z and Y.
Have you seen the rig experts? The little, that's a picture from mine.
Yeah, that's the basic one.
Yeah, it's really basic, but it's a good tool to.
Yeah, for the what you're doing with the antenna analyzer, it's fine.
Yeah.
It wouldn't help you much in trying to figure out what stub length you need to match something. I don't think. Okay, so
Easier than a.
there's a lot of words there. Basically saying that all the good stuff about Smith charts is kind of outside the scope of the exam. You just need to know the basics, which are the resistance circles and the reactance arcs. And I'll show that, I think, on the next one. And the way the Smith chart was developed, some guy named Smith, of course, took a regular Cartesian coordinate plot of resistance and reactance and decided to make it into a circle. So that's why the resistance axis is the same. Okay, and it's the horizontal axis. It didn't change. It's the real axis. The rest of them are the imaginary, and they got, in wrapping this thing around into a circle, they change into arcs of constant reactance. And then we have constant resistance circles on it. So it's just a combination of circles and arcs that intersect.
So the arc, the reason for the circle is that the changing frequency.
Wavelength.
Well,
Yeah.
yeah,
All right. It's a quarter wavelength halfway around the circle.
Quarter wavelength, halfway around.
So at one end of the resistance axis, okay, you have on the left, normally, it's 0 ohms, 0 resistance. On the other end, it's infinite, okay, quarter wave. You go all the way around again, half wave, you're back to the starting point. So if you went from 0 around, it's 0. If you went from infinite back around to infinite. The center is they call the prime point, which is 1. Okay, because you normalize, this isn't in ohms, it's normalized. So if you want to do it for 50 ohm system, whatever reactances you have that you've measured that you want to plot, you divide it by your characteristic impedance. So if you were in 50 ohms, you divide everything by 50. So 50 ohms turns out to be 1 right in the center of the Smith chart. And 0 is still 0, and infinity is still infinity. And in fact, when you do a network analyzer, like VNAs, the little ones, or even with a rig expert, if you calibrate it, you do 3 points to calibrate it. You do short, open, and 50 ohms, which are those 3 points on the Smith chart.
I have to skip out on the rest of this one.
Huh?
So I gotta skip out on the rest of this one. I gotta get to my daughter's house.
Okay. We only got one after this, so.
All right. I'll see you next week.
Figure it out.
Well, all right,
take care, John.
Have a wild party without it.
So
Yeah.
like was mentioned, I don't know why they decided to show these rotated 90 degrees because you never see it that way.
Yeah, they found it, yeah. And I kept reading it and reading it and rereading it, thinking, I didn't know if I was misunderstanding what I
No,
was reading.
they
Or
just-
if they put it in there.
The
Yeah.
whoever made these from the exam questions decided it looks better that way or something. I don't know. Hey, Bruce.
Almost missed the party.
So
While you're talking that.
yeah, I didn't bring my VNA. I can't show it.
Well,
But that's next week anyway.
well, it'll give you time to play with it before the.
Oh, I have one.
You have one of the boards? Okay.
And in fact, you can do the calibration with that board. It has open, short, and features.
Yeah.
And 50 ohms. All right. So beside the fact that they always show it rotated 90 degrees from where you would normally do it, it still works the same. So you see the major axis, which is vertical here, going from 0 to infinity with 1 in the center. So that's your normalized resistance. So if you're doing 50 ohms and you divided everything by 50, then 50 ohms comes out to be 1. And you see there's a circle that intersects. That every point on that resistance circle is, in this instance, 50 ohms or 1. Likewise, if you go up to 0.5, every point on that circle is 0.5 real resistance. The fact that you get to the left or the right in this, instead of up and down, it's going to be inductive, in this case on the right, capacitive on the left. So where those arcs, which are constant reactance arcs, intersect the resistance circle, those are your R plus R minus JX points. And you divide your X by your normal impedance, like 50 ohms.
So do the arcs erode away your antenna?
Are the arcs what?
Or the arcs
Pay no
erode away
attention to
your
him.
antenna?
Yeah.
It's another vibrant non-second.
Mhm.
Okay, so like they say here, 0 should be on the far left if they showed the stupid thing right. And I did it this way because that's the way it is on the exam. And infinity's on the far right. So those are the basic things. The prime axis, which is resistance, the constant resistance circles, constant reactance arcs. And the outer circle, if you notice, is 0 ohms.
That really is unnecessary to put that like that.
I have no idea why they did.
Talking resistance is, your straight resistance is vertical.
I have no idea why.
Every one I've ever seen is rotated,
Yeah.
clockwise 90 degrees.
What type of coordinate system is used in a Smith chart?
Bravo.
Right. I would, for some reason, I don't consider that a coordinate system, but
No.
yeah, it's plotting resistance circles and reactance arcs. So what are two families of circles and arcs that make up a Smith chart?
Charlie.
All right. On figure 9.3, what's the only straight line shown that should be horizontal?
Delta.
And that's actually the exam question.
Yep, this is exactly what's on the exam.
Wow.
I guess
Could we,
it's to see if you really understand it.
yeah, maybe so.
If you memorized it this way, maybe you don't understand when you rotate it. I don't know. Okay, anyway, the arcs are constant reactance. And depending on your chart, you may have many more arcs plotted so that you can get a more accurate thing like the one I printed out. It's a lot of arcs.
It's busy.
Um, the outer circle, okay, that's zero resistance is also the reactance axis, because the fact that they took a rectangular chart and folded it around in a circle. So your normal y-axis, instead of being vertical versus horizontal, or horizontal in this case, is a circle. So that makes it somewhat confusing, but you really don't need to worry about the arcs and the circles. So when the resistance axis is horizontal, not like they've shown, positive reactances or inductive reactances are going to be on the top, and capacitive are going to be on the bottom. In this case, it's right and left, just to confuse you.
Right.
So what do the arcs on the Smith chart represent?
Doggy.
Constant reactance. Okay, what's the name for the large outer circle on which the reactance arcs terminate?
Bobby.
Huh.
Okay, so I mentioned before we use normalized resistance and reactance. So if you're working in this example of a 50 ohm system, you divide everything by 50 ohms. Therefore, it becomes like if you had a 50 plus J100, you're going to plot it as 1 plus J2. So you've normalized everything to 50 ohms. So after you've used the Smith chart to maybe figure out the length of a stub, then you have to multiply your result back by 50 to find out what it is in terms of the real impedance. And you do that with the prime center, which is the center of the circle, which represents the normalized impedance. In this case, we're using 50 ohms. That one represents 50 ohms.
But you could use it for 75 ohms.
You can do it with any one you want. You just have to divide everything and then multiply everything. They did that so that the chart isn't dependent on impedance. You can use it for any impedance you want.
Right.
So what's the process of normalization with regard to a Smith chart?
Prime center, Charlie.
Charlie sounds good.
Let's waiting for these guys to answer.
All right, so what are Smith charts often used for? You can calculate the impedance along a transmission line. The chart they show doesn't show wavelengths, which normally you see plotted along the outer ring. So it's a quarter wavelength for half the circle, or half a wavelength all the way around. So you can figure lengths that way. You can calculate the SWR. And in some cases, that one has an SWR kind of circle added. What you normally do is you need a compass to work with the Smith chart normally, because you'll have to draw some circles like a SWR circle.
You have to orientate to north.
Is what? Yes. That's why they did it, so they pointed north.
There you go.
That's why they rotated it.
Everybody's thinking of the companies.
Which of the following can be calculated using a Smith chart?
Alpha.
But these guys, look
Impedance.
at that. Look at the backside. That'll tell you the various things you can read on.
Which of the following is often determined using a Smith chart?
Let's see if that's the same one I've.
Charlie.
Charlie.
It has to go snap in, fault the loading.
That's actually a question. That's a dead giveaway
Yeah.
question.
Some questions are easy, some are not.
Alpha.
Okay. Another application is figuring out length and position of a matching stub. The wavelength scales, which they don't show on their chart, is calibrated in fractions of a wavelength. Like I said, it's halfway around the circle is a quarter wavelength, all the way around is a half wavelength. And they also use the direction, whether you go clockwise or counterclockwise. So when you figure out what the length of your stub is going to be, okay, then you have to multiply it by the velocity factor to find out the physical length of it.
Let me ask you guys a question. You know what SWR effectively is? It's amount of voltage, it's amount of power reflected back from the load.
All right. Which of the following is a common use for a Smith chart?
Alpha.
What'd you pay for that? I think mine was like $10 on Amazon.
This late one with the two cables was 22. Like,
Ooh.
everything is just exchanged as a mess now.
Yeah.
Especially stuff.
There was a nano VNA at that show yesterday,
Oh, there was?
but it had a lot of cable. I mean, there was,
Well, you need a little adapter cables to do
no,
anything.
but there were so many cables in that kit, you couldn't even zip it.
I think that has more on it than mine does.
The thing you have to keep in mind is the length of the cable is ultimately important on this. Now, I have the bigger,
Well,
Yeah.
that's why you calibrate it with the board.
right, but I have a nano VNA plus because my eyesight's not as good as it once was. And it's got a 4-inch screen on it as opposed to the little 2.5-inch screen. But it's got type N connectors instead of these SMAs.
Yeah.
Okay, so how are the
$30 more, it's worth it.
yeah. How are the wavelength scales on a Smith chart calibrated?
Don't remember.
Yeah, it's a funny way to word the question, actually.
Fraction of electrical wavelength? D.
I wouldn't have called it calibrated. But they're in fractions of a electrical wavelength. And of course, they never show you the chart with the wavelength scale on it.
It's like they say about radar. It never lies, but sometimes it misunderstands the question.